Hi there. Welcome to Sig Figs and Measurement Uncertainty for the Sciences. Well, let's get started. In this first video, we're going to look at rules for handling sig figs in measurements, and then we'll look at sig figs in numbers and in calculations. I should say at the outset that there are two kinds of numbers that are known exactly and numbers that are inexact. Now, exact numbers are counted values or defined values, such as a kilogram is 1,000 grams. That's defined and it's exact. 1,000 meters in a kilometer, exactly 12 objects makes a dozen. So exact numbers have an infinite number of significant figures, and they will never limit the precision of a calculation. We're going to spend the rest of our time on this video talking about inexact numbers that are either measured or calculated values. So how do we determine sig figs in measurements, which are an example of inexact values? Well, first you need to appreciate the difference between measurements taken from a digital scale versus measurements taken from an analog scale. Measurements taken from a digital scale are known with certainty, so there's no uncertainty in digital readings. This electronic balance displays exactly 3 sig figs, 4.57 grams in this case. This digital thermometer displays 36.8 degrees Celsius precisely. There's no need to estimate a value on the instrument. So all the digits read from a digital scale are significant. In this example, both have 3 sig figs. We can also say there is no reading error or reading uncertainty from digital scales. Now, we're not saying that these instruments are accurate. That may not be the true mass or the true temperature. It's not accuracy. We're simply saying the readings are certain. There is no uncertainty in taking these readings. Next, we're going to look at measurements taken from analog scales, for which the last sig fig will have to be estimated. So how do we determine sig figs in measurements from analog scales? Well, as I just said, analog scale readings have some degree of uncertainty. When we take a measurement from an analog scale, the number of sig figs that we can report includes all of the digits that we know with certainty plus the first uncertain digit. Important rule. So I have here a couple of analog scales representing automobile gauges. I have the engine temperature in degrees Fahrenheit and the speedometer in kilometers per hour. Let's go ahead and read these scales and record the reading that we would estimate the number of sig figs and the uncertainty in taking those readings, and I'll explain as we go. So in the first case, the gauge reading for the engine temperature, well, this is 180 Fahrenheit, this is 190, this is 185, 184, and 183. So we can see for sure that the temperature lies between 183 and 184. So what temperature is that? Well, I would report 183.7. So I know the 1 and the 8 and the 3 are for sure, and I include in my significant figures my first estimate, which I say is 0.7. So the number of sig figs is 4. The 1, the 8, the 3 for sure, and the first estimate 0.7. Now the reading uncertainty, check the definition. We try to read analog scales to 1/10 of the smallest division. So if the smallest division here is 1 Fahrenheit degree, a tenth of that is 0.1. So I'm going to say the reading uncertainty is plus or minus 0.1. Now whenever you record an uncertainty, it has to have the same level of precision as the reading itself. Now the level of precision here is to the decimal of a Fahrenheit degree, likewise here. So let's try the next one. Here I have the speedometer. What's the speed you see on here? Well, 80, 90, 100. I have divisions every 5. This is 95 kilometers per hour, and this is 100. So I would estimate it's between 95 and 100. I'm going to say it's about 98. How many sig figs is that? Well, that's 2 because I have the 9 is known for sure, and the 8 is my first estimate. Now, when I want to record the uncertainty in the reading, I'm going to say that's plus or minus 1, meaning the number could have been 97 to 98 or 99. Now, if you, in fact, try and apply this rule of 1/10 the smallest division is 5 degrees, and a tenth of that would be 0.5, you'd be reporting plus or minus 0.5. You can't do that. 0.5 has more precision, a higher level of precision than, say, 1. So when scales have coarse divisions that are difficult to read, instead of reading to 1/10 the smallest division, you could try 1/5 of the smallest division. And if that's too coarse, or still, you might want to use 1/2 the smallest division. But in this case, I think 1/5 would be adequate. And 1/5 of 5 degrees is 1. And so 1 plus or minus 1 kilometer per hour. And that is consistent with the precision of the reading. More about this to come. Let's get some more practice. Let's measure the length of this gray object using 3 different rulers, ruler A, B, and C, and we will record the length, number of sig figs, and reading uncertainty for each. So reading using ruler A, there are very few divisions. We can estimate the length to be greater than 1 meter, but not as large as 2. So I'm going to estimate this about 1.1 meters, I'll say. I'm guessing that this distance beyond the 1 is perhaps 1/10 of the tire distance from here to here. It's my best estimate. Number of sig figs in this reading, I hope you recognize that's 2. We know the 1 meter for sure, and the decimal 1 is our first estimate, but it's significant. What about the reading uncertainty? What would you say? I think that's plus or minus 0.1. Plus or minus 1/10 of the smallest division. So we're saying the reading is somewhere between 1.0, 1.2, our best guess. Notice how the precision of the uncertainty matches the precision of the reading. They're both in the first decimal position. If we use a more precise scale, scale B, we should be able to get a more precise measurement. So in this case, we can see the length of the gray object is 1. Well, it's less than 0.1, so it's 1.0 something. I'm going to guess that's 1.08. Number of sig figs is 3 because I know the 1 and the 0 for sure. The 8 is my first estimate. For the reading uncertainty, I'm going to say that's plus or minus 0.01. 1/10 of the smallest division. The smallest division is 0.1, so a tenth of that is in the hundredths place. Notice again that the consistency between the reading uncertainty in the hundredths or second decimal place and also in the reading. Now, as we use better and better scales with higher precision, we can read values to higher precision. In case of scale C, you can read the length of the gray object to be 1.0, not quite 0.9, it's 0.8 something. So I'm going to estimate that's 1.089. Sig figs in that, 4, because we know the 1, the 0, and the 8 are here for sure, and the 9 is my first estimate, but it is significant. As far as the reading uncertainty goes, I would say plus or minus 0.001, so we're in the thousandths decimal position in both the reading and the uncertainty. So this is, again, 1/10 of the smallest division. The smallest division would be, well, here's 1 meter, a tenth of a meter, a hundredth of a meter, and a tenth of that would be a thousandth. So 1/10 the smallest division. So in general, the smallest unit we can exactly measure is the smallest division of our measuring instrument. We may then estimate 1 digit more. All of these and only these digits are significant digits or sig figs. So take a look at this beaker. We see divisions at 20, 30, 40, 50, 60, 70, 80. Every 10 mils is a division. So to read the volume in the beaker, I can see that's between 40, less than 50, between 40 and 50 mils. So the digit 4 is significant because we know it with certainty. Then we have to estimate the second digit. Now, for example, or for sake of argument, I'm going to say this is 47. And 7 is an estimate, but it's significant because it's the first uncertain digit. So when we read the volume, we read to 1/10 the smallest division, and this applies to any measurement. With discretion, we mentioned already that if the graduations are coarse, meaning they're so close together they're harder to read, you might choose to read this to 1/5 of the smallest division or 0.2 of the smallest division. If the graduations are very close, then you might have to read it to 1/2 or 0.5 the smallest division. So just use discretion. Whatever's reasonable works. So the reading uncertainty is 1/10 the smallest division. The smallest division is 10 mils, and 1/10 of that is a mil, so therefore my reading uncertainty is plus or minus 1 milliliter. So my estimated volume is 47 mils. You might have read 46. Your friend might have read 48. All three of these are correct. They all contain one uncertain digit, the 8 or the 7 or the 6, and they all are within the reading uncertainty of the scale of plus or minus 1 milliliter. So the volume with its uncertainty should be reported as follows. You would say 47 plus or minus 1 mil. And this would be correct to 2 sig figs because both the 4 and the 7 are significant. So let's read the volume in this graduated cylinder. First thing you notice is that the surface of the liquid is curved, and that is called a meniscus. As a brief digression, what causes that? The water is creeping up the sides of the glass, and the reason for that is the attractive forces between the water and the glass, which are called adhesive forces between two different materials. Those forces of attraction are greater than the cohesive forces of water to itself, and so because the water is so strongly attracted to the glass, it tends to climb up the sides in narrow containers. In any case, let's get the reading. We want to read a meniscus at the bottom of the meniscus, and the smallest division on this graduated cylinder we need. So notice this is 35, this is 40, 5 divisions, this is 36 and 37 and 38, so our smallest division is 1 milliliter. We would estimate this to be between 36 and 37 mils. We take our best estimate. 1/10 the smallest division is 1/10 of a mil, so that would be to the nearest 0.1. I would call that 36.5 milliliters. Now, an equally precise value would have been, say, 36.6 or 36.4 plus or minus 0.1. So how many sig figs does that have? Well, it has 3, because the 3 and the 6 are known for sure, and the first estimate, 0.5, is also significant. Let's read the volume on the burette. So notice in the case of a burette, the volume increases moving down rather than going up as we saw in the case of a graduated cylinder. What are these divisions? So this is 20 mils, 21 mils. I see 10 divisions between those. This is 20.5, 20.4, 20.3. So we can say that the smallest division on the burette is 0.1 milliliters. So if we're going to estimate the uncertainty, that would be 1/10 the smallest division. A tenth of 0.1 will be 0.01. So our reading uncertainty should be plus or minus 0.01. And just look at that. Even if you forget the rule, just look at it and convince yourself that you're going to estimate between 20.3 and 20.4. You're adding an additional decimal. You will be in the second decimal position or the hundredths place. So a good reading here might be 20.3, not quite 20.4. I'm going to say 20.38 plus or minus 0.01. Notice again how the precision of the uncertainty is in the same decimal place as the precision of the value. You need to keep those consistent. So an equally precise answer might have been 20.39 or 20.37. How many sig figs does our answer have? Well, it has 4 sig figs because the 2, the 0, and the 3, the 2, 0, and the 3 are all known for sure, and only the 8 is being estimated. Yeah. All right, let's summarize and state some important rules. We've seen that the last sig fig that is reported in a number is the first digit that is uncertain. So the 7 in 47 is the last sig fig that's reported, and it's the first digit that is uncertain. We've seen that measurements should be written in the form result plus or minus an uncertainty, such as 47 plus or minus 1 mil. However, when we encounter a number without a stated uncertainty, say for example we just read the number 47 mils, what level of precision or uncertainty can we assume is present? Well, if 47 is a calculated number, we can assume it was rounded from a number that was greater than 46.5 but less than 47.5. Or if 47 came from a measurement, we would assume a reading uncertainty of plus or minus 1 on the last digit. In other words, a range between 46 and 48 mils. And if we don't know, we have to assume the latter case, the greatest uncertainty, which would be plus or minus 1 on the last digit. Another important rule, do not report more than one sig fig in an uncertainty. For example, a volume of 47 plus or minus 1.0 makes no sense. You can't report two levels of uncertainty. Remember, uncertainty is an estimate anyway. You can't have two estimates of the uncertainty. Only one sig fig in an uncertainty. A number with its uncertainty must have the same level of precision. So for example, a temperature of 23 plus or minus 0.2 makes no sense. These have different levels of precision. If in fact you can read the temperature to the nearest decimal degree, then you should report to the nearest decimal 23 point something. Now 47 plus or minus 1 mil or 23.6 plus or minus 0.2 Celsius degrees, those correctly report uncertainty to one sig fig. And the precision of the number and the precision of the uncertainty are consistent here, and that's what we want. Additional digits should be carried through calculations to minimize rounding errors. And one additional digit may be written as an intermediate result. We call this a guard digit. Guard digits are usually subscripted or underlined. For example, the 4 in 23.64 is subscripted or underlined, indicating that it's an additional degree of uncertainty, an estimate that we're just carrying for the purpose of minimizing rounding errors, but that guard digit will be rounded out in the final answer. In the last slide, we looked at the scenario if we encounter a number that's not one of our own measurements, it's simply a number we read in a book. How do we know how much precision is in the number? In this slide, we're going to look at a similar case. Let's say we're presented again with a number that's not our own measurement. It's from a book. How do we know how many sig figs are in the number? Well, it's actually quite simple. To count sig figs in a number, we start at the left-hand side of the number and simply move right until you reach the first non-zero digit. So in the number 0.0068, we start from the left and we start counting when we reach the first non-zero digit, which is the 6. In the case of 3.020, we start at the left, and in fact the first digit here is non-zero, so we start counting here. Likewise in 4090, the first non-zero digit on the left is the first digit, the 4, we start counting here. So we start counting at that digit. Zeros to the left are never significant. Now, where do you stop? Well, the digit at which you stop counting depends upon whether or not there's a decimal in the number. Now, if there is a decimal in the number, you count all the way to the end of the number. For example, in 0.0068, we start at the left, we start counting sig figs on the first non-zero digit. There's a decimal in it, so we just count right to the end. There's 2 sig figs in 0.0068. In the number 3.020, we start counting sig figs at the 3. There's a decimal in the number, so you count right to the end, 4 sig figs. Now the other case is if the number does not have a decimal, then you count to the last non-zero digit. So in the number 4090, we start counting at the 4, but we stop at the 9. There's no decimal in the number, so zeros to the right of the last non-zero digit are not significant. In the number 3.5 million, start counting at the 3, stop at the 5. There's no decimal, so zeros to the right are not significant. There are 2 sig figs in this number. So to summarize, we count sig figs starting at the left at the first non-zero digit. If there's a decimal in the number, then count right to the end. If there's no decimal, then count to the last non-zero digit. So here I'm going to restate the rules for sig figs in a different fashion. Hopefully it helps. So first of all, non-zero digits, that is 1 through 9, are always significant. For example, 6.2, these are non-zero digits. There are 2 of them. There's 2 sig figs in the number. 16.2 has 3 non-zero digits, so there are 3 sig figs. 16.25 has 4 non-zero digits, or 4 sig figs. Leading zeros, that's zeros on the left, that appear at the start of a number are never significant because they only serve to fix the position of the decimal point in a number that's less than 1. For example, 0.564. This 0 to the left is not significant. This has 3 sig figs. 0.0564. Zeros to the left are not significant. Only the non-zero digits are. There are 3 sig figs. What about confined zeros? Zeros that appear between non-zero digits. Well, they are always significant. So for example, in 104, the 0 is significant. There are 3 sig figs in that number. In 1004, confined zeros are significant, a total of 4 sig figs. And finally, trailing zeros at the end of a number are significant only if the number contains a decimal point. So 15,400 contains no decimal point, so zeros to the right are not significant. This has 3 sig figs. 1540.0 does have a decimal point, so zeros to the right are significant, so a total of 5 sig figs. 15.4000 has a decimal, total of 6 sig figs. Okay, let's get some practice. How many sig figs do you count in each of these numbers? 345 has no zeros. They're all non-zero digits, so they're all significant, 3 sig figs. 32,000 has no decimal, so trailing zeros are not significant, only 2 sig figs in that number. 0.0078, zeros to the left are never significant, so only 2 sig figs. 9.0068, confined zeros are always significant, so all of these digits count. There are 5 sig figs. 5.020 has a decimal in it. Zeros to the right are therefore significant, a total of 4 sig figs. 10,700 has no decimal, so zeros to the right are not significant, a total of 3 sig figs. 122.0 has a decimal, so zeros to the right are significant, a total of 4 sig figs. 10.04, confined zeros are always significant, so 4 sig figs. 20 has no decimal in it, so zeros to the right are not considered significant. We would report 1 sig fig. 0.604, zeros to the left are not significant. Confined zeros are, a total of 3 sig figs. Sig figs are easily handled by scientific notation, so let's talk about scientific notation. The number of particles in a mole of substance is Avogadro's number. It's a very large number, as you can see, written in common notation. Now I've only listed this number to 4 sig figs. There are more currently known, but this will serve our purpose for what we're teaching here. In scientific notation, this number is 6.022 times 10 to the 23rd. So in scientific notation, only sig figs are shown. There's only 4 sig figs in this number. So in scientific notation, a number has 1 non-zero digit to the left of the decimal and is multiplied by the appropriate power of 10. Now if the original number was greater than 1, then the power of 10 will be positive. If, however, the original number was between 0 and 1, then the power of 10 will have a negative exponent. Here's a term that you should be familiar with. The order of magnitude is simply the power or exponent of 10, and it tells how big or small a number is. So consider or compare 10 to the 9 and 10 to the 6. We can say that 10 to the 9 is 3 orders of magnitude, or 3 powers of 10, or 10 cubed times larger than 10 to the 6th. So to express a common number in scientific notation, we move the decimal so that only one non-zero digit is left of the decimal. Then we multiply by the appropriate power of 10 to tell how far the decimal has been moved. Take a look at this number in common notation, 6008.25. To convert this to scientific notation, we have to move the decimal 3 places to the left to get 6.00825, and we multiply by 10 cubed since we moved our decimal 3 places to the left. If we take a small number in common notation and convert it to scientific notation, the process is the same, except that you would move the decimal to the right, and the power of 10 would then be negative. So in the case of 0.000513, we need to move the decimal over 4 places to the right to produce 5.13. And since we move the decimal to the right, we have a negative exponent, 10 to the minus 4. So a negative exponent is used for small numbers, a positive exponent for large numbers. Now the reason I'm stressing this is because I have seen cases where students simply memorize a process, but when we go from scientific notation back to common notation, that process gets reversed and it's easy to get confused. But if we remember the magnitude of the numbers, it helps us here. So let's think of this. If we had 0.001, it's a number less than 1. It can be expressed by a negative exponent, 10 to the minus 3. Does that help? A number less than 1 will be expressed as an exponent that is negative. So let's consider here 0.001 can be written as 1 over 1,000, which is 1 over 10 to the 3. And you probably remember from algebra class that 1 over 10 to the 3 can be expressed as 10 to the minus 3. So a negative exponent corresponds to a value that is between 0 and 1. So let's get some practice. Let's convert these numbers from common notation to scientific notation. We have 68,090. We'll have to move the decimal over 4 places to the left, and so we're going to have a number times 10 to the 4. This number is greater than 1, therefore it has a positive exponent of 10. Now, furthermore, the 0 to the right is not significant because there is no decimal in the number, so that 0 would not be carried into scientific notation. It's simply 6.809 times 10 to the 4. 0.00023 will have to move the decimal over 4 places, actually 5 places to the right. So we're going to have 10 to the minus 5 as the exponent. This number is less than 1. It should have a negative exponent. And therefore it's 2.3 times 10 to the minus 5. 5,400 has to have the decimal moved 3 places to the left. So it'll be 10 to the 3, a positive exponent, because this number is greater than 1. Now we're not going to report the zeros because the zeros to the right are not significant because there's no decimal in the number, so it's simply 5.4 times 10 cubed. Decimal 80 requires we move the decimal 1 place to the right. It'll be 10 to the minus 1. This 0 is significant because there's a decimal in the number, so it'll be 8.0 times 10 to the minus 1. 0.05040, we'll have to move the decimal over 2 places to the right, so that'll be 10 to the minus 2 as a power. This number is less than 1. It'll have a negative exponent. Furthermore, the 0 to the right is significant because there's a decimal in the number, so it should be carried into the scientific notation, giving us 5.040 times 10 to the minus 2. Now when we go from scientific notation to common notation, it's a little bit easier. Remember that all of the digits shown in scientific notation are significant, so they'll all be carried in. We don't have to worry about dropping any zeros. So 7 times 10 to the minus 1, we simply move the decimal over 1 place to the right. We'll have 70. In this number, the 0 is not significant. There's only 1 sig fig, the same as in this number. 4.098 times 10 to the minus 3 requires we move the decimal 3 places to the left. We'll have 0.04098. 8.3 times 10 squared. We're going to move the decimal 2 places to the right. Will give us 830. This 0 on the right is not significant. It's not shown in a scientific format either. And finally, 10.1 times 10 to the minus 2 requires we move the decimal 2 places to the left, and that will give us 0.101. So we've learned how to handle sig figs in individual numbers, but what about when the numbers are combined together in a calculation? How many sig figs do we report in our final answer? So it depends upon the mathematical operation you're performing. We'll look first at the case of multiplication, division, roots, and powers. And the rule is that we round off the answer so it has only as many sig figs as the value in the calculation with the fewest number of sig figs. So consider this example. I have 35.63 with 4 sig figs times 0.5481 with 4 sig figs times 0.0530 with only 3 sig figs divided by 1.1689 with 5 sig figs multiplied by 100%. The calculator would tell us the answer is 88.5470578%. But you wouldn't report that number, right? You'd report 3 sig figs, you'd report 88.5 because the answer will contain only as many sig figs as the number with the fewest number of sig figs, which is right here, and that's 3 sig figs. Well, then you ask, well, what about the 100%? Doesn't that contain only 1 sig fig? Well, remember that 100% is an exact number. It has an infinite number of sig figs, and therefore it will not limit the precision of an answer. Well, let's get some practice. If we multiply 250 with 2 sig figs times 0.100 with 3 sig figs, our answer will have 2 sig figs. Multiplying by 0.1 moves the decimal over 1 place. We'd report 25, which just has 2 sig figs. 2.000 with 4 sig figs times 4040 with 3 sig figs. We're going to double 4040 and we'll report 8080, which just has 3 sig figs. This final 0 is not significant because there's no decimal in the number. 72.0 with 3 sig figs divided by 0.010 with 2 sig figs. We're going to have an answer with 2 sig figs. Dividing by 0.01 is the same as multiplying by 100, so we'll get 7200, and this number has 2 sig figs in it. Root of 25 with 2 sig figs will be 5 with 2 sig figs, so that's 5.0. 4200 has 2 sig figs times 0.01 with 3 sig figs divided by 2 with 3 sig figs. So there'll be 2 sig figs in our answer. 4200 times 0.01 moves the decimal over 2 places. We have 42 divided by 2 is 21, simply 21 with 2 sig figs. 9.00 has 3 sig figs. When we square it, we'll get 81.0, which has 3 sig figs. And finally, the square root of 16.00 times 4.0000, we have 4 sig figs as a minimum. So 4 times 16 is 64. The square root of that is 8. And so we'll have 8.000, which has 4 sig figs. So we've seen that in the case of multiplication, division, roots, and powers, we report our answer to as many sig figs as the number with the least number of sig figs in the calculation. But for addition and subtraction, it's different. The answer here is only as precise as the least precise measurement, which is another way of saying that the answer will have as many decimal places as the value with the least number of decimal places. Let's give an example. Say we have 3 volumes of liquid added together. Let's say we take 6 milliliters of liquid that's in a beaker. We estimate the volume to be 6 mils, plus or minus a mil. Then we add 18.7 mils using a graduated cylinder to that, so we have a little better precision. Then we add to that 0.76 mil delivered from a burette. It has higher precision still. If we want to know the total volume, we could add those numbers together and come up with 25.46 milliliters. But in truth, that's not really accurate. Note that the least precise measurement in our group here is 6 mils. It's only reported to the nearest milliliter, that's plus or minus a mil. And therefore, the answer really can't be reported with any greater precision than that. It can't have any decimal places because neither does the 6. If you think about it, when we say 6 mils, we mean plus or minus a mil. That means it could be anywhere between 5 and 7 mils that was originally in the beaker. So for sake of argument, the total volume really then could have been not 25.46, could have been 1 mil less or 1 mil more, could have been anywhere between 24.46 up to 26.46. And so really we need to round that to the nearest milliliter. We report that as 25 milliliters. So when you round off your answers, so that it includes only the sig figs as we have done, you may note that the answer now has more or less sig figs than one or more of the original measurements. For example, 25 mils has 2 sig figs, and it's more than 6 mils, which only has 1. That's okay. Remember that the answer to addition and subtractions, we are counting decimal places, not sig figs. Let's get some practice. Adding 4.5 with 6.2, each of these numbers has 1 decimal, so our answer will have 1 decimal, 10.7. 21.2 minus 12.0, each has 1 decimal, and so will our answer, 9.2. Again, notice here that we start out with numbers with 2 sig figs. Our answer has 3 sig figs. Here we go from 3 sig figs down to 2. It's not about sig figs for addition and subtraction. It's about precision. It's about precision. In the case of 123.4 plus 10, no decimals and 1 decimal. So even though the answer technically is 133.4, we'll have to drop the 0.4, report only to the nearest milliliter. 8 decimal 0, 0, 0, 0, minus 68.0. Well, technically that's minus 60, but since we only have 1 decimal in this number, we can only report 1 decimal in our answer. Let's summarize what we've learned in this video. So zeros to the left of a decimal are never significant, as in 0.005 only has 1 sig fig. Zeros to the right of the last non-zero digit only significant if the number has a decimal in it. So this 0 is not significant. It's to the right of the last non-zero digit. So this 0 is not significant, only 1 sig fig. Now I saw this recently in a text and I wanted to show it to you. 50 decimal implies or indicates that this 0 is significant. This is a nice, convenient, concise way of showing that the 0 is significant without having to write this in scientific notation. So this has 2 sig figs. Scientific notation displays only significant figures with 1 digit to the left of the decimal raised to the appropriate power of 10. So 120 would be 1.2 times 10 squared. For addition and subtraction, the answer has as many decimal places as the number with the least number of decimal places. One decimal and 3 decimals, we add it to 1 decimal. For multiplication and division, roots and powers, report only as many sig figs as the number with the least number of sig figs. Digital measurements have no reading uncertainty. Record all digits that are displayed. Analog measurements do have uncertainty in their last sig fig. Report all the digits you know for sure, plus 1 estimated digit. When possible, estimate the last digit of a measurement to 1/10 the smallest scale division. If the scale is too close together, then try 1/5 the smallest division. If that's still too coarse, try 1/2 the smallest division. As far as the reading uncertainty goes, it's reported as plus or minus 1 on the smallest unit reported in the measured value. So for example, in 47, the smallest unit reported is in the ones column, so your uncertainty is reported in the ones column as well, plus or minus 1. Report uncertainties to just 1 sig fig. This would never be 1.5 or just 1 sig fig in your uncertainty. report a number to the same precision as the uncertainty. So 1 sig fig in the number, 1 sig fig in the uncertainty. So you completed part 1, sig figs and measurement uncertainty. Thanks for watching.